It is that 80% was Braden's sample proportion. Is everybody with me so far? What symbol do we use for the sample proportion? P hat. Okay. All right. Now, we had n equals 5, n equals 10, and n equals 24, right? Okay. What are some of the key, what do you guys think are similar about all of these graphs?
Their shape.
Their shape? Okay. What else? I mean, I would argue that this one is very strongly skewed. This one's maybe a little bit less. And this one's getting kind of, I mean, it might have a little bit of skewness, but not a ton. Okay? So as the sample size is going up, it kind of feels to me like the skewness is different. What else is similar? The mean, give or take. If I asked you guys to estimate the mean of this one, why is that? This one, what would you say? 0.3-ish? Like here-ish? Okay. What about the one with my sample size being 10? Similar-ish. And sample size of 24. Similar. Is everybody with me? Okay. All right. So, P is the population lag. And sometimes when we're describing the population value, we call it the true value. True proportion of pink in the bag. And based off of our 3 graphs, we might call that 0.3. Based off of what our graphs are telling us. Is everybody good? Okay. And P hat is equal to the different sample proportions. So, are you guys with me? Like, I labeled this as n equals 24, n equals 10, and n equals 5. But in reality, this was a distribution of P hats. So what did we do? We took a population. We took repeated samples of that population. Is everybody good? What is the variable here? What's changing? The sample proportion is my variable. What's staying the same? There was only one. The proportion of the population. Is everybody with me? Okay, so P is a constant. P hat is a variable. And something that feels really weird, this is practically opposite of when you learn the word variable in say, for instance, Mrs. Turner's class, okay? When you guys get a variable in an algebra-based course, a variable is a letter, right? And we use that letter to stand for a number we do not know. Is everybody good? Okay? In statistics, the parameter, the P, is the number we don't know, and our variable is the value we do know, right? Because in the real world, we take one sample, and we have the value from our sample. Does that make sense? What is variable is whether or not our sample matches our population or not. And you guys, do samples ever match the population?
Samples are not perfect.
Everybody good? Do we need to say this together again? Okay. Samples are not perfect. So I'm going to tell you right now, your sample does not exactly match your population. Our hope is that it comes really, really close. Everybody good so far? What's the difference between these graphs? Certainly we could see maybe that skewness is getting, like, the bigger the sample size, there's less skewness. What else? When we compare different graphs, we compare shape, we compare center, we compare spread. Is the spread the same? Okay, so what's happening as my sample size increased? The spread is decreasing. Is everybody good? Okay. So, for the larger sample, the variable, the different possible p-hats, were more symmetric and less spread out. Now, Braden, I hate to keep picking on you, but you had the best sample, okay? Yeah. You guys, how come we did not get an 80% pink for n equals 24 versus n equals 5? The larger your sample is, the more likely it is to resemble your population. We're comfortable with that. The larger the sample, the more likely it is to resemble the population. So this 0.8 of Braden's is a one-off, man. He just got really lucky. You know how hard it would be to get a sample of 24 starbursts out of that bag that were 80% pink? That would be way harder to do. Everybody good? All right. Now, these graphs, I didn't do this because I'm not a jerk, okay? Could I also have made you guys weigh every single one of your starbursts and find the average weight of your sample? Do you guys get what I'm saying? So instead of all these graphs being p-hats, we'd have a graph of x bars. Is everybody good? Okay, great. So x bar would be the sample mean weight. Would we all have the same sample mean? No, because samples are not perfect. Okay. The mu would be the true mean weight. How many true mean weights to the bag were there? Exactly 1. The number we know is the variable. And again, that can feel a little bit weird. Okay. Now, way back when, in like August, we talked about standard deviation. So if we look at this graph and I ask you to describe the shape, the center, the spread, we would say it is skewed to the right, because remember when we described skewness, we described the tail, with a mean of about 0.3. Everybody good? Okay. So, standard deviation, if you guys recall, what the standard deviation is like these points are all this distance from the line, right? And this point right here is a much larger distance from the mean. These ones have their own distance from the mean, etc. Is everybody with me? Okay. Standard deviation was the average of those distances. Everybody good? Okay. So, if our goal is to take our sample and say what percent of the bag is pink, our samples were close but not great, right? Not perfect, but for the most part, we're pretty darn close to that 0.3, for the most part, yeah? Okay. So we did have some error due to sampling alone, just the fact that samples aren't perfect. We call that sampling error. And the standard deviation is the average of those sampling errors. Is everybody good? All right. So, these distributions are what we call sampling distributions. That is a distribution created from lots of sampling. And the standard deviation of those we don't call it the standard deviation, we call it the standard error. What is the average my sample is away from the true value? So, we will eventually have lots of formulas to calculate standard error. There's known predictable things, okay? But my big idea here is that samples have variability, and that that variability is measured by what we call the standard error, which is really just how off our samples are from the fact that they're samples and not perfect. You guys, did we do anything wrong with our sampling? You guys didn't get to pick your sample, right? I was looking you in the eyes as I put it on your table most of the time. It was a truly random sample, okay? We didn't do anything wrong, even though sometimes we got lucky Braden who gets to get his 80% pink starbursts. Everybody good? Like there was nothing wrong with that process. There is just sampling variability. Everybody good? Okay, great. Proportion of the getting. All right, so, you guys, I spent more time on the previous page than normal. We're going to cross out this whole section because that whole section is what I just told you. Does that make sense? All right. So, at the beginning of the school year, we had that giant box of pennies from Dr. Lee, right? And you guys had to take different samples. And one of the things I asked you to find was the mean year, okay? Here are the results of your graphs, of your data from over the time, okay? All right, now, I did two things here. I gave you the graphs, and then I also gave you the mean and the standard deviation, which really is what we just learned is now called the standard error, okay? And one of the things, if I asked you guys, what is each one of these, like this bar goes up to what looks to be about 22, yeah? Just to make sure we're understanding, that means there were 22 values whose X bar was in between 1983.5 and 1989.1. We good? Just, all right, so there's 22 different X bars inside this column. And there are 6 X bars in this one, et cetera, et cetera, et cetera. Everybody good? So this was us I wanted to give you guys a concrete example of repeat sampling. We each got a different sample, okay? What do you notice about the means of each of these? They're pretty close, yeah? And we could use those to guess that the mean year of the entire box was probably somewhere around 1988, 1989, okay? Based off of these different groups. All right, what do you notice about the standard deviation? First two are similar, though certainly as my sample size is increasing, my standard deviation is decreasing, yes? All right. So, as n increases, the standard deviation, the standard error decrease. Now, typically, it's hard to see in this because these were all fairly normally distributed, okay? The shape, as we increase sample size, the shape typically gets closer to normal. And in fact, the whole reason we study normal distributions in statistics class is that is how X bars and P hats tend to behave with large sample sizes. Okay? Now, these two ideas are what we call the central limit theorem. Any of you guys in calculus? Anyone? When pre-calc, did you guys use limit notation yet?
Not yet.
You haven't done anything with limits? Okay. All right. Okay. So, limit just means as something is happening, what else is happening. Okay? So, as my sample size is increasing, here's as we look through, my biggest p hat here got compared to my biggest p hat here, that those outside edges creep towards the center because my sample is more likely to match my population. Okay? So, what essentially central limit theorem says is those numbers, the p hats, the x bars, the measurements I'm taking from my sample get closer to the real value. Okay, so if you are asked, why would you want to take a larger sample? Your answer should say something like p hats are closer to p. On the aggregate, all the possible p hats are closer to the actual value, or all the possible x bars are closer to the real value. Now, we also really like that normality because the more normal something is, the more predictable and easier to use. Okay? But large sample size means less variability in x bar or p hat, meaning x bars are closer to mu, p hats are closer to p, which is what we want always and always and always. All right. Sorry. Should have been here. Same idea. Okay. That's a huge idea. We like to say there is less variability in our estimator. That's the best way to say that. Okay? Less variability in our estimator. Sophomores. Any of you born in August? Sophomores. Are you a sophomore? Oh. Okay. August what?
29.
August 29th. So let's see. I really hate this. I don't want to do what I'm about to do. What year?
2009.
August 2009. Anybody born earlier than August 2009? I'm trying to find the youngest one of you in the room. Youngest in the room. Oh, after. Yeah. Sorry. Pretend. Let's pretend your teacher actually understands how time works. So I'm trying to find the youngest person in the room. Callie, when's your birthday? 2011. April 2011. Anybody later than April 2011? Okay. So, Kelly, that makes you 14? Okay. Who's the oldest person in the room? No, for this purpose, we're including me. Are we all comfortable saying I am the oldest person in the room? Okay. So we have the youngest person being 14. And we have the oldest person being 25. It's totally it, 25. I could say 23. 23 is how many years I've been teaching. So start adding that up. But I am not somebody who's ashamed of their age, so 45. Okay? Everybody good? So if this is our population, this whole room, what is our population range? 45 minus 14. So 31. I should have written my age on top, right? I should have put my age on top. That would have made that math a little bit easier. Okay. All right. So you guys, here's what we're going to do. There are not symbols for the population range and a sample range. So I'm going to call this big R, and we're going to take some samples where little r is going to be this sample range. Is everybody good? One, two. You guys you just need to write down your number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. Everybody good? Everybody's got a number. And here's what we're going to do. I'm going to take a random sample of 5. So, you guys, if I needed a random sample of 5, I need a random digit. Is everybody good? Should I have a reason I want to use this one instead of the one on my iPad here. So, because the calculator has a rand int no repeat. Is everybody good? So for my lower, I'm going to put 1. For my upper, I'm going to put 25, and I'm going to generate 5 digits. Is everybody good? All right. If I say your number, raise your hand. Cool? 24, 23, 4, 13, and 11. All right. Alex, how old are you? 17. Anybody older than 17? And then Callie is 14. So what is the sample range for that group, 17 and 14? 3. All right. Now, if I took a different sample and measured the range of that different sample, we good? I'm going to do it again. 19, 2, 9, 25, 6. 17. And then keep your hands up, guys. How old are you?
I'm 16.
16? Okay, so range of 1. Is everybody good? Now, you guys, I'm going to keep doing this, right? How often are we going to get a sample range of 31? Could it happen? What would need to happen? I'd have to be in the sample. And Callie or somebody else who might be 14, right? There might be. Is Callie the only 14-year-old? Okay. All right. So, do you guys catch my drift on this? Okay. So, rather than continually doing this, are we comfortable saying that this graph would look like this? Give or take. We all comfortable with what that graph looks like? Okay. So, you guys, based off of this graph, do you guys think our sample range is a good predictor of our population range? Why not?
A lot of people in their 20s or 30s.
Okay, now, let's pull me out of this for a second. Population range would become 4, right? I'm still going to make an argument. 3, population range might be 3, okay? If our population range is 3, we pull this out. Does this graph do a good job estimating the population range? Okay. Now, are you guys comfortable saying that the sample range is always probably a little bit smaller and at best equal to our population range? Are we comfortable with this idea? Okay. So when we were looking at these graphs, like of our p-hats, you guys were comfortable saying that the proportion of the bags were somewhere between 25 and 30%. That felt pretty good to you, right? Okay? And I totally agree with you. That is a great estimator. Okay? So we talked about bias in Unit 3 when we were talking about like voluntary response bias or non-response bias, right? There is also estimator bias in that not just because you can measure something of a sample doesn't mean that is a good representation of the population. This is a great example of it. Okay, so we like to use unbiased estimators. And what makes an estimator an unbiased estimator is that the mean of the sampling distribution, in other words, the mean of the p-hats or the mean of the x-bars, because those are the two we're going to spend almost all of our energy on, okay? The mean of the p-hats and the mean of the x-bars equals the true value, so equals the population mean or the population proportion. Okay, so we work primarily with p-hats and x-bars to estimate p and mu. We do that specifically because those are unbiased estimators. The sample range is biased because of what we just talked about. I had wanted to put that picture in your head, okay? You guys, I took a sample size of 5 from our group, yes? Would this graph look all that different if my sample size was 10? I'd probably have less down here, right? But this would still be pretty weird to get. And so what we don't like about this is the mean of this does not equal the sample or the population range, right? Okay. So larger sample size does not decrease the bias of the estimator. It decreases the variability of the estimator. Everybody with me? So if I'm kind of narrowing this down, the sample range is less than the population range usually. So the mean of the sample ranges does not equal the population range. And that's what you would hope to happen for an unbiased estimator. All right, so a larger sample size is less variability, not less bias. To reiterate one more time, why would we want less variability? If we're taking a sample and we have to, that's the sample's all we got to use it to represent our population. Less variability would mean the p-hats are closer to p. And the x-bars are closer to mu. That makes our life, in general, way better because our sample looks closer to our population. Do we know whether we got like a crazy, like as I look at this, when we take our sample, do we know that we got one of the ones that was close to the center versus ones out on the end? We don't. But we know that overall, on the aggregate, they're closer, which means our estimation is probably closer. Are we good? Nice work today. Guys, when I talk about